Crepant resolutions of Calabi-Yau orbifolds. So a Calabi-Yau for today's talk will be a Keller manifold with trivial canonical bundle. So the canonical bundle is the top exterior power of holomorphic forms on the manifold. And the fact that it is trivial tells us that we have a non-vanishing holomorphic N0 form. So, omega non-vanishing. N4. Now, when you try to construct these Calabi-Yaus, it turns out that usually you cannot construct them to be smooth right away, and you'll get singular Calabi-Yaus. And the easiest type of singularity you might have is an orbifold singularity. The easiest type. Now, how do you think about an orbifold singularity? Locally, this is modeled on Cn mod G, where G is a finite subgroup of SLN C. So why this condition? We know that the Calabi-Yau has a holonomy SUN. And now, locally, you'll want this group, you'll want the quotient also to have holonomy SUN. And then this is why you need a finite subgroup to be in SLNC. OK, so these are the singularities we are interested in. And what can we do with them? We want to smooth them out. And one way to resolve these singularities is to perform a resolution of singularities. So what's a resolution? You take your singular guy, Cn mod G, and you resolve it to obtain another complex manifold. And this guy pi is a biholomorphism on dense open sets. It turns out that there is a very precise way according to which the canonical bundle behaves under this resolution of singularities. So the canonical bundle of X will be the pullback of the canonical bundle of the singularity. I'll just write it, Kcn mod G, plus some stuff coming from the exceptional divisor of the resolution, which we call discrepancy. Now, when we perform such a resolution of singularities, we would really like to get back a Calabi-Yau. So if we want a Calabi-Yau, this guy should be equal to 0. And we started with a Calabi-Yau orbifold, so this is equal to 0. So in order to have a Crepant resolution, we must not have discrepancy. In order to have a Calabi-Yau structure, we must not have discrepancy. And that's what Crepant means. So X is Calabi-Yau is equivalent with the fact that we have no discrepancy, which is equal to a Crepant resolution. So Crepant resolutions are the guys which will give us back Calabi-Yau structures. Now, there are two natural questions. The first question is, when does such a resolution exist? And then if it exists, is it unique? And then the second type of question is, how can we describe the topology of a Crepant resolution? Now, the answer to question number one really depends on the dimension we are in. For n equals 2, it turns out that a Crepant resolution always exists, and it is unique. For the case n equals 3, also Crepant resolution always exists, but it is not unique. And the reason for this is that in complex dimension 3, we have what's called flops. And what's a flop? A flop, you can think of it if in our complex three-dimensional manifold, we have a CP1. So we have a rational curve. We can contract this CP1 to form something singular, and then blow it up in the other direction. So I'll blow it up like this, and I'll get another CP1. So this process of blowing down, of contracting a CP1 and then smoothing it, resolving it in the other direction is called a flop. And then for the case n equals to 4, actually, in this case, Crepant resolution do not exist most of the time. So Crepant resolutions actually greater or equal than 4 might not exist. And the reason for this is that the singularities will be terminal. which means that there will be no way to make that discrepancy 0. That's a terminal singularity. All right, so in the next part, I'll focus on the case n equals to 2, and I'll try to give you the answer to the second question. And after that, we'll do the case n equals to 3. So case n equals to 2. In this case, so G is a finite subgroup of SL2C. And the singularities C2 mod G, these were studied in 1884 by Klein. And then they are called Kleinian singularities. Or they are also called rational double points. Or sometimes Duval singularities. It depends on the paper you are reading. If you look at the finite subgroups of SL2C, it turns out that we have 5 families. So 5 families of G. And they are the cyclic group. Then you have the binary dihedral groups. The order of this guy is 4K. And these are 2 infinite families. And then we have 3 special groups, which are the binary tetrahedral group, which has order 24, the binary icosahedral, order 48, and actually, this is binary octahedral. And then the binary icosahedral, which has order 120. So how do you think of these 3 exceptional groups? We look at finite subgroups of SL2C, and because they sit in SL2C up to a conjugation, we can think of them as being in SU2. And SU2 is a double cover of SO3. So in SO3, you can look at the tetrahedron and take the symmetries of the tetrahedron and leave them up to SU2. And that's the binary tetrahedral group. And then you do the same thing for the octahedron or the icosahedron, and you get a finite subgroups. All right, but what can you do with this? I mean, how can you help us to figure out the topology of the Crepant resolution? Here came Mackay, which, if we look at the irreducible representations of G, what you can do is, because G is a finite subgroup of SL2C, then G has a 2-dimensional representation coming from that inclusion. And then you can tensor it up with one of these irreducible representations, and then decompose this into irreducibles. So then you'll get Aij Rj. And what Mackay noticed is that Aij are 0 or 1, so that if you if you like draw a dot for each of the irreducible representations. So for example, here I have R1, R2, RR. And then I join two irreducible representation with an arrow. If that Aij, the corresponding Aij is 1, then what I will get in the cyclic case, I'll get something like this. In the dihedral case, I'll obtain something like this. In the tetrahedral case, we'll get octahedral case. And in the icosahedral case, we get and these are exactly the simply laced Dynkin diagrams. So this is AK minus 1, this is DK, this is E6, E7, E8. So Mackay correspondence really gives it gives you a correspondence between the finite subgroups of SL2C and the simply laced Dynkin diagrams. And actually, a little bit more can be said. If we take this matrix of the entries Aij's, which is called a Janssen C matrix, then it turns out that if you take A minus 2 times the identity matrix, what you get is C, the Cartan matrix. Associated to the Dynkin diagram. So really the representation theory of the finite subgroup encodes everything about the Dynkin diagram and the corresponding Lie algebra. Now, as I said over here, if I take C2 mod G, a Crepant resolution always exists and it is unique. So let X be the unique Crepant resolution of C2 mod G. Then the exceptional divisor of this X is going to be the dual of the Dynkin diagram. So what does this mean? If, for example, how do I construct a dual? For example, if I take E6, the dual means I replace each of the dots by a rational curve. And then two rational curves intersect transversely if and only if these dots are joined by a curve. So the dual there will be something like this. Dual of E6. So the exceptional divisor is a union of CI's, I from 1 to R. CI intersect transversally. And are rational curves. their self-intersection turns out to be -2 because of this condition to be Crepant. And moreover, these classes Ci, they form a basis in homology in H2 of X, coefficients in C. And the intersection pairing Ci times Cj is the negative of the Cartan matrix. So what's the moral of this picture here? Is that the Dynkin diagram completely describes the topology of the Crepant resolution. It gives us the structure of the exceptional divisor, and it gives us the intersection pairing in homology. But you can be picky about it and say, oh, but in order to get to the Dynkin diagram from the finite subgroups, you really use the representation theory. And in this picture, the representation theory doesn't show up at all. So how do we get around that? So we are looking for a geometrical interpretation. My calculus models. And in order to do this, we start again from the irreducible representations. And each irreducible representation will give rise to a holomorphic bundle over X. So these are bundles which at infinity have the fiber Ri. I mean, these are non-compact things. And like. Now, it turns out that the first check classes of this bundle form a basis in cohomology H2 of X. And then if you take products in cohomology, so things like this, multiplying together two Chern classes, getting a fourth form, and integrating it over X, this matrix is nothing else than the inverse of the Cartan matrix. So this basis is a basis in H2 dual to that the basis given by CIs. And this geometrical interpretation was given by Gonzalez, Springer, and Verdier. And Verdier using case-by-case analysis. And another proof, more general proof, was given by Kronheimer and Nakajima. Using gauge theory techniques. So this is a picture in dimension 2. Now, let's move to dimension 3 and try to answer to the same questions. I mean, what's going on in this case? So, case n equals to 3. So, as I said, a Crepant resolution exists. But not unique. However, these Crepant resolutions have a few things in common. It turns out that all of them have the same Euler number and the same Betti numbers. And these are what's called the stringing Orbifold Euler and Betti numbers. And they were introduced by Dixon, Harvey, Waffa, and Witten. And what's really cool about them is that they can be entirely expressed in terms of the finite subgroup G. Entirely expressed in terms of G. For example, if you take the Euler number, this is the number of conjugacy classes of G. And there are similar formulas for the Betti numbers. All right, so physicists had predicted the Euler and Betti numbers, but nobody knew if such a resolution could be constructed. And until the beginning of the 90s, so existence early 90s, a bunch of people like Ito, Rowan, and Markuszewicz they constructed case-by-case Crepant resolutions. Case-by-case existence. And then in 95, Nakamura came along and he conjectured that a Crepant resolution of C3 mod G is given by a certain Hilbert scheme, which we call now the Nakamura-Hilbert scheme. And this is Hilb GC3 is a Crepant resolution. So what's this Hilbert scheme? So if you look at C3 mod G, you look at the action of the group G on C3, then you have the orbits. And generically, an orbit will consist of if you denote the order of G by n, generically an orbit will have n points. And you take the set of all such orbits and you close it, and you get this Hilbert scheme. And it turned out that it was really hard to prove this theorem, this conjecture, until 99, when, so proved, completely proved in 99. by Bridgeland King and Reed using derived categories techniques. And then another result in terms of existence was last year when Crow and Ishii they conjectured that all the Crepant resolutions of C3 mod G can be realized like modular spaces. All Crepant resolutions of C3 mod G can be expressed as moduli spaces. So with this, we
Sorry, I just want to be sure. So this was a conjecture in O2, or they claimed?
Actually, it's still a conjecture in the general case. They just prove it for the abelian case using.
Can they make a more specific conjecture than just the moduli spaces?
Oh, the moduli spaces are some sort of like they are related to the Hilbert scheme description. So they have a really they are in terms of quiver varieties and stuff. So now the question is, we have all these now a lot of Crepant resolutions in some cases. How do we tell them apart? I mean, how do we differentiate between two Crepant resolutions? And so this is the next question. How to differentiate between two Crepant resolutions. And in order to answer to this question, I mean, we would like to have something like the Mackay correspondence. But it's just that if you try to construct something like a Dinkin diagram associated to the finite subgroup, you can push it a little, but not too much. So what you can do is you can try to you can take a Crepant resolution and like over there, I can take the reducible representations of G. And they will give us some holomorphic bundles. Over our variety, X. But now, what's known also from this work of Bridgeland, King, and Reed is that, so BKR also implies that these bundles, these holomorphic bundles, Ri, form a basis in K theory. So then, by taking the Chern character, you'll get a basis in H upper star of X. you still don't know how this distributes on different pieces of H upper star of X, but they will give you a basis. So then the hope is, I mean, since all this is valid for all the Crepant resolutions, then the hope is that you can differentiate between two different Crepant resolutions by looking at the multiplicative structure. Because at the level of the group structure in cohomology, you cannot distinguish because the Betti numbers are the same. So, idea, look at the multiplicative structure. In H upper star of X, or K theory if you want. Now, how can you do this? The idea will be to use index theory to get information about multiplicative structure, because you try to multiply together two Chern characters, and multiplying Chern characters takes you to index theory. But first, in order to do index theory on these Crepant resolutions, you need to understand a little bit about their geometry. So, need to understand the geometry of X. So now I'll make an assumption, because almost everything I'm going to say now works just in this special case. I'll assume that G acts with an isolated singularity. On C3. And why this assumption? Because in this case, theorem 1, the Crepant resolution X has a Ricci flat an ALE Ricci flat. ALE Ricci flat metric. So we already know that it must have a Ricci flat metric because it's a Calabi-Yau. But I want a special kind of Ricci flat, which is ALE. So what does it mean to be ALE? It means that if I take C3 mod G, and I look at it, so because G acts as an isolated singularity on C3, then when you look at the orbifold, there will be this very singular point at the origin, but then the end of your guy will look like pretty much C3 minus a point mod out by this group. It will be fairly smooth. It will be a piece of the Euclidean space, locally Euclidean, and it will kind of grow asymptotically. So, ALE means that X resembles R6 minus the origin mod G at infinity. And in order to prove this theorem, you need two steps. Step 1 is to realize X. So realize. Actually, this proof is based on work of Sardo-Inferi, who first studied this ALE matrix on Crepant resolutions. And he was a student of Kronheimer, so his work is based on Kronheimer's construction of ALE gravitational instantons. So what we can do is, step 1, realize X as a simplicity reduction. And this is reasonable to expect because in the cases I am in, the Crepant resolution has a moduli space description. So then you can think of it as a simplicity reduction. And then step 2, use this simplicity reduction and apply the proof of the Calabi-Yau conjecture for ALE manifolds. Because realizing X as a simplicity reduction will give us an ALE structure. And then the proof of the Calabi-Yau conjecture will give us a Ricci flat metric in that Keller class. And this proof belongs to Tian and Yau, and also Joyce. So you put these things together, and you get your Ricci flat metric. So now that you have an ALE Ricci flat metric, you are ready to start to think about index theory. Oops. So what's index theory about? I mean, if you have a holomorphic bundle on your as you've seen in the gauge theory lecture, you can construct a Dirac operator and here I'll take just the half Dirac operator. We are on a 6-dimensional guy, which is Ricci flat, so it is spin. So we take the positive spin or bundle tensor E, and the Dirac operator takes us into this space as minus tensor E. Now, usually when you do index theory on a compact manifold, you'll extend your operator to in your space of functions in the L2 norm, and then you'll get Fredholm results, and you can compute the Fredholm index. Here, because we are on an ALE manifold, you have to take a little bit of care of what's going on at infinity, so then you'll use weighted Sobolev spaces and stuff like that. But theorem, in the appropriate completion, D plus is Fredholm, and its Fredholm index so when you do index theorem, you expect to have a guy, a topological guy, which is the Chen character times A hat genus. But now, because we are on a non-compact manifold, you have to have a contribution from infinity. And that's called eta invariant. So this guy is a spectral, it's a spectral invariant of the bound of the, somehow you can think of this manifold as a manifold with boundary at infinity. And you look at the spectrum of the Dirac operator restricted to that boundary. And that spectrum will give you the eta invariant, which is some sort of zeta function. But what's really nice about this formula is that here, if you replace this bundle, holomorphic bundle E, by one of these bundles, Ri tensor Rj, then since the Chern character is multiplicative, you will get some information about the multiplicative structure in cohomology. So, but for this we need, if I want to use this term of the formula, I need to understand the index and the eta invariant. And then another theorem, it's a vanishing result, which says that the index is actually 0. And then another proposition, which is some sort of Lefschetz fixed point formula, is that the eta invariant is expressed in terms of the finite group I'll denote by chi the character associated to the representation E, chi I. And then when we are on, because G is a finite subgroup of S of 3C, here we'll get minus this standard representation on C3, plus I have another three-dimensional representation. And this is the eta invariant. So it's a pretty nice formula once you replace this, because then it tells you that the integral formula is equal to the eta invariant. So apply this for E equals Ri tensor Rj. And then what you are going to get is then consequence is that once you do some yoga with that formula and with the A-hat genus, you'll get that the Chern character minus the rank of the bundle Ri times the Chern character Rj minus the rank of the bundle Rj. This matrix will be a matrix C to the minus 1, where, how do I define this matrix C? This matrix will show up in the same way the Cartan matrix showed up for the Dynkin diagrams. So what we do, we take the irreducible representation, we tensor it with C3, decompose this, and get Aij Rj. But now you have another three-dimensional representation. So you can also take lambda 2 C3. And now this decomposition, I'll denote Bij Rj. And I'll get my generalized Cartan matrix as being the matrix with entries Aij minus Bij. Generalized. Cartan matrix. So then this part of the product is the inverse of the Cartan matrix, which, if you look back at your notes for the case of n equals 2, it's pretty much the same formula. I mean, in that case, if you take Chern character minus the rank, you'll end up with just C1 of Ri. C1 times C1 of Rj is equal to the inverse of the Cartan matrix. So this is the generalization. Of Markov correspondence. N equals 3. But now, if you look at this formula, if you look at it, you can notice something which is very funny. This part of the intersection product structure in cohomology is, you can express it just in terms of the finite group G, so it doesn't depend on the Crepant resolution you are on. So, remark 1. The formula does not depend on the Crepant resolution. So you cannot really use it to distinguish between different Crepant resolutions. I mean, it's nice, but... And if you try to fix it, what's there that we still need? When you do this Chern character minus the rank, what you are left here, you have a piece in dimension 2 in the 2 cohomology and in the 4 cohomology. And here the same. So in here, you will never get elements like, if you want to go, that formula doesn't contain elements like C1 cube of an Ri. Do not show up in this formula. And the reason for this is that in getting this formula, I was somehow trying to get rid of the A-hat genus, because I didn't tell you how to compute the A-hat genus. Now, if you want to get such formulas for C1 cubes, which is, by the way, the Yukawa coupling, you can go back to the index formula and replace our bundle E by Ri. So what you will get C1 cubed Ri up to some constants plus integral C1 Ri, the first Pontryagin eigenclass, which is C2 of x, is equal to eta Ri over 2. So then what you really need is a formula for this guy. And this is actually work in progress right now. Progress. Now, we need we need some sort of a junction formula over there. It's also known that there exists a partition on the group G by what's called age. So it's not really important right now what age is, but it is a partition. And this age, since G is a finite subgroup of SL3C, age of an element takes values in the set 0, 1, and 2. And then you can describe the Crepant resolution, the Crepant divisors. Divisors are in one-to-one correspondence with elements of H1. Equal 1. So when you want an adjunction formula, this, if I have a Crepant divisor, I'll associate it to an element G with Hg equals to 1. Then it turns out that claim integral over x C1 of Ri C2 of x is alpha Ri of G times the second Chern class of the Crepant divisor corresponding to G. And this element, alpha Ri of G, is entirely expressed in terms of G. Of G. But this element, C2 of the Crepant divisor, really changes when you perform a flop. So then here, with this element, C1 cubed of Ri, you will distinguish between different Crepant resolutions. All right, that's it.
To understand the geometry of X, people have recently used a technique called motivic integration.
Yeah.
There are famous results of Kontsevich and Baturev and so forth. Kontsevich on the stringy Hodge numbers and Baturev on the McKay correspondence. Can you say a few words of how that ties into this whole story?
I mean, it doesn't tie into this. I mean, it ties in the part of the existence of a Crepant resolution. But the motivic integration and stuff like this doesn't give you any information about the multiplicative structure in cohomology or K-theory.
What is Baturev's result again on the
Baturev is getting results about the stringy. I mean, he shows that he defines the stringy Hodge numbers, and he shows that every Crepant resolution has these stringy Hodge numbers. But to my knowledge, it doesn't. I mean,
I thought that was Kontsevich's result, the independence of stringy Hodge numbers on the Crepant resolution.
I don't know. Other questions? Yeah.
So the index is 0. How do you?
That's a really tricky argument. It has to do with the weighted Sobolev spaces, and the fact that we have an ALE Ricci flat metric. And the argument, I mean, you choose your weight, and you take your Dirac operator completed in this weight, so it will go L2 alpha, L1 alpha, S plus tensor E, L2 0 alpha minus 1, S plus tensor E. But then when you take the dual of this operator, turns out that the dual will be L2, it will go from 5 minus alpha. When you dualize, when you take the adjoint of this operator, so then this will go S minus tensor E, L2 whatever, S. This is S minus, this is S plus, sorry. But now, since you are on a threefold which is Calabi-Yau. S plus is lambda 0, 0 plus lambda 0, 2. And S minus is lambda 0, 0, 0, 1 plus lambda 0, 3. So they are equal. And this guy is nothing else